this. So Thursday you're going to take the quiz over those 4 sections. If you recall, 5.7 and 5.8 were pretty basic. So 5.6, the fundamental theorem of calculus. Can you integrate a function? Plug in the upper bound minus the lower bound. 5.9 was pretty much the same thing, except you have to do an extra step of a U-substitution. So do the U-substitution first, and then either change your bounds in terms of U and plug it in, or go back in terms of X and use your original X bounds. So we're going to do some examples of that today in class. So this is pretty straightforward. The way the semester works, I'm not going to have a chance to quiz you again, but I want to quiz you over 6.1 and 6.2 before you take the exam 4. So what I'm going to do is I'm going to post 6.1 and 6.2 probably the end of this week, and it will be due Tuesday by 11 a.m., meaning before exam 4. It's going to be due Tuesday before you take exam 4, right? So instead of doing Monday at midnight, you can have up into, so if you want to stay up all night, that's fine. But I know sometimes midnight or 11 comes faster and you just sit down at 10 and you really use some extra time on that. So as long as, this quiz will be due before you take exam 4, which I think will benefit you once you get to exam 4. And that will be on Wiley. Exam 4 will be the Tuesday, which is kind of weird, but that will be Tuesday 5.7. That's going to cover 4.8 to 6.2. So I'll have a chance to quiz you over everything on exam 4 before you take exam 4. Wednesday is the last day of class next week. Thursday and Friday are reading days, and I'm still looking at setting up a 2-hour block in the ILC like we did last semester, where anyone from Calc 1 can come. All the other Calc 1 instructors will be there. There's only 2 of us, but you can have blank final exams from different semesters that we've just had extra, or you can bring your own copy of the final exam and sit down and try to take it. That way you can put yourself in that mindset and kind of psychological, you have the chance to ask other instructors questions. You can ask your neighbor questions. You can work together. You can talk about various things like that. And hopefully by that time I'll have some worked out examples of final exams that don't have answer key that I talk about where students go wrong. Like, here students do this and it's cost them points, or various things like that. So you can watch those hopefully before that date and get some idea of how to prepare for the final exam. And then a week from Saturday, so May 11th, will be your final exam from 10:30 to 12:30, probably in 101 or 111 Royal Hall, but that's not set yet. Generally, something I have to go and look into. I hope everything's in order, but the coordinator is the one that coordinates that question.
Is 2 hours normally plenty of time for people?
Yeah, I have those that stay the 2 hours and want more, but generally you can do everything in 2 hours. I have students 30 minutes, they're done, and they do fine too. So
How many questions?
there's usually about 17 questions. If you look at old final exams, you can pull that up.
So it's not like always a set number?
It's not always a set number. It's always 200 points though. So you can see if you just look up, if I look at 3 of them, just to kind of get a feel. This one has 15 questions. This one has 17 questions, and this one has 18 questions. Generally, the first page is multiple choice. You don't have to show any work there. But if you look at old final exams, they always kind of follow the same format, so hopefully if you get used to taking them in that, generally there's 1 or 2 problems that has never been on a final exam before, type of problems that have never been on a final exam before. But then there's 4 or 5 problems that are always asked. And then the rest are just kind of interchanged. So there's usually always a L'Hopital's rule problem where you have to identify it's L'Hopital's rule problem. There's limits. There's usually always an equation of the tangent line problem, or find the slope at a certain point. write an equation on the tangent line. So you need to find the derivative, plug in x equals 4, that's your slope, and then you're given a point. So your x is 4. If you plug that into the function, you get your y. Point, slope, that's all you need for the equation of the tangent line. So knowing that formula. Basic derivatives. There's always, can you differentiate a page of functions? Product rule, quotient rule, chain rule type things. Derivative of ln x, derivative of sine of x, e to the x, cosine of x. And that might be mixed in with product rule and chain rule and things like that. And then here's the L'Hopital's rule problems that are generally, it follows the course as well. The beginning is what you learned in the beginning, and the end is what you learned at the end. So sometimes people work in backwards because the end stuff's so fresh, they go to the last page, do that, and then go to the beginning. But, I mean, your own method is what you have there, whatever you feel. There's usually always an application or two problems, one or two application problems. Usually it's a related rate or a maximum minimize, or both. So some kind of related rate problem or some kind of maximum minimum problem where you have to maximize or minimize a function you have to come up with. Question.
I haven't looked at the final exams for the integration problems yet.
Mm-hmm.
Are there ones on there that we should be able to do?
At this point, you should be able to do everything but the last page or two of a
Okay.
final exam. So here, compute the definite integral. This is a U-substitution, so really it's 5-9. We're going to do something like that in class. But you do the U-substitution, you either change your bounds on U, and you plug it in terms of U, or you do the U-substitution, integrate it, find the antiderivative in terms of U, replace that back in terms of T, and use your original T bounds. But yeah, we're going to talk about the last 2 pages, usually is from chapter 6. And after this week, you should be able to do any of them. Question?
Just can you tell me the difference between horizontal tangents and the horizontal asymptotes when you're solving?
Horizontal asymptotes are the end behavior of the function, right? So what the function approaches as x goes to infinity. It would be a limit. Horizontal tangents are when does the derivative equal 0? Of what value x does the slope equal 0? So in this function, if I graph it, if I have something like this, let's just have it like this. Let's say this is x equals minus 5. This is at x equals 0. This is a horizontal tangent. This is a horizontal asymptote. The graph of the function is approaching minus 5 as x goes to infinity. X equals 0 gives me a horizontal slope. The equation of the tangent line is horizontal. This is, let's say this is f of x. This is where f prime of x equals 0. The slope is 0.
Yeah, like the tangent equation is going to have a point that's actually on the function.
Correct.
Or that'll asymptote, it never touches.
Correct.
Okay.
Not that it never touches it, because
Well,
it can cross it.
Sure.
Right, I could have a function that does this, where it crosses the horizontal asymptote. But that's really pre-calculus.
Okay.
The calculus part is, can you find the value in which the horizontal tangent is 0? This is going to also be a maximum, or a relative maximum. If I had something like this, this is also a point which you have a horizontal tangent line, and this is a minimum. And there's different ways to approach that. But yeah, horizontal tangent is a point in the graph when your slope is 0. A horizontal asymptote is the end behavior. What is this function approaching as x goes to infinity? Those are different concepts. Generally, there's a definition of the derivative. The last couple semesters, that's been something that's been on the final exam. I don't make the final exam, so I can't be too exact what's on it, but what I've seen in the past, I'm just making those connections, saying there's usually always an equation of the tangent line. There's usually always derivatives. There's usually always a L'Hopital's rule problem. Equation of the tangent line could also be presented as local linear approximation, because that's exactly what it is. Local linear approximation is the equation of the tangent line at a point. We're going to talk about some of these in Chapter 6. Integrate, compute the integral. This function is negative from -2 to 0 and positive from 0 to 1, so you can rewrite that. You can graph. There's multiple different approaches to it. Integrating this, you guys did an example of this on Wiley, I think. This is basically tangent inverse. So the inverse functions that will come up will only be tangent inverse or sine inverse. You won't have anything other than being able to identify this is a tangent inverse or a sine inverse. And the same thing with derivatives. They'll only ever ask you to differentiate tangent inverse or sine inverse and then integrate tangent inverse or sine inverse, if that's something that pops up. Question?
Are we going to have the definite integral problems with the sigma?
No. 5.4 will not be where they want you to do the sigma notation. That will not be covered on the final exam. How would you approach this problem? I gave you one of these on your quiz.
Separated out.
Yes. Do not try to do a U-substitution. It's not a U-substitution problem, right? You're going to write 2x squared over x cubed plus x cubed, or 3x over x cubed, and that simplifies to 2 over x plus 3 over x squared. When you integrate 3 over x, you get 3 ln of absolute value of x. And then when you integrate 3 over x squared, you get 3x to the minus 1 over minus 1 plus a c. So generally, I've seen in the past something like this where you're left with 2 over x somewhere, because when you integrate that, you get ln of absolute value of x. Versus everywhere else you integrate, you get just the power rule, right? This would be 3x to the minus 2. When I integrate that, I get 3x to the minus 1 over minus 1. So I know I'm kind of hitting these fast, but at this point, it should be somewhat coming to you of like, yes, this is making sense. So yeah, there are 8 final exams you can put yourself through, and you can see probably on every single one of them there's equation of the tangent line problems. So 8 different equation of the tangent line problems. Basic integration problems. And usually the last page or two is Chapter 6, which we'll get to this week.
Do you make a study guide for the final exam? Or do you use it regularly?
A lot of times I just put all 4 of them together in one study guide that I kind of highlight some things, but of course I can't cover everything. I star the things that I've seen in the past. But yeah, I'll break it down to saying this is what you covered in Chapter 1, this is what you covered in Chapter 2. And that way sometimes it's just nice to be like, when did I talk about L'Hopital's rule? You can refer back to the, oh, it's in this chapter. And star kind of the things that I've seen in the past. Okay, so anyone have any questions on the next 2 weeks? Quiz 11 is just kind of a bonus quiz, and that will be on Wiley. Exam 4, cover 4.862, and I know it's kind of fast turnaround. Take exam 4, get it back on Wednesday, and then take the final on Saturday, but keep everything fresh, right? And then the written homework will be due this Friday by 5 p.m. I'll give it back to you on Monday. Monday we'll review. Tuesday take the exam, get it back on Wednesday. So really that last week of class is just kind of, there's really no lecture. Okay, so let's look at some problems in 5.9. So you guys are section 5. No, you guys are actually section 2. Oh well. So the first one, it tells you what to use as u. And I think you guys done this one either on the written homework back before we talked about definite integrals. So once you get it, you integrate in terms of u, you can change your bounds. If I change my bounds and u is ln of x, what are my u bounds? So the ln of e to the 5th, which would just be 5, and ln of e to the 25, which is 25. So I go 5 to 25 of u, right? Which is a lot easier to integrate in terms of u and plug in 25 to 5 than going back in terms of x and plugging in e to the 5th, e to the 25th, and e to the 5th. But you have both methods there. So we've seen an example of this.
Is that because do you equal 1 over x?
Yes. So let's go ahead and write this one out. So this is number 3b. So if I'm integrating e to the 5th, e to the 25th of ln of x over x dx. And they tell me to use u to be ln of x. So once you pick your u, you're locked into what du is based on u. So du is 1 over x dx, which is nice because that is exactly what I have here, right? I have dx over x. So I can just replace that with du. So one thing to keep in mind in 5.9 is you have to change your bounds of integration in terms of u if you don't want to go back in terms of x. So this is really method 2. And that's kind of the method I prefer because I can convince myself I can plug in a number to an equation and get out 2 numbers versus going back in terms of x and plugging in the original bounds. So here I usually like to tell myself I've already changed my bounds of integration. So this would be 5 to 25. This would be u to du. Right? So this is u squared over 2, plug in 25 and minus 5. So I have 25 squared over 2 minus 5 squared over 2.
Is that, oh, never mind, sorry.
Right, because the fundamental theorem of calculus says I plug in my upper bound minus my lower bound. So what would be 25 times 25? 625. So 625 over 2 minus 25 over 2, which would be 600 over 2, which would be 300. Question?
So when you plug in the bounds in terms of u, you do not have to back substitute
Correct.
for x?
Yes. Yeah, because these are u-bounds. So it's basically, let's go ahead and say method 1. Method 1 would say, now if I turn it back in terms of x, I would have ln of x squared over 2, and then I would plug in my original bounds, e to the 25th, e to the 5th, which ends up ln of e to the 25 is 25, right? So I still end up with 25 squared over 2 minus 5 squared over 2. So I get the exact same thing as I did with method 1. I don't have to back substitute in terms of x. If I do, then I use my original x bounds. But if I want to leave it in u, I can integrate it in terms of u, find the antiderivative, and use my u bounds. And that's why I like to point this out. I'm using u bounds here, so I don't have to worry about it being in terms of x. Common mistake, probably the most generally point deduction from this is integrating in terms of u and using x bounds. And you forget to change your bounds of integration. So I like to just tell myself, I need to make sure I get this in terms of u. And so when I write that, I don't just copy e to the 5th and e to the 25.
That's all you have to do?
Mhm.
Yeah, there's no like plus C or anything.
There's no plus c because this represents the area underneath the curve,
Okay, got it.
which would be a finite number
Right.
and not a general function for an antiderivative.
So basically what you're doing is you take the e to the 5 and you plug it into ln of x.
Yes.
Take the e to the 5.
So this is my relationship between u and x. So if x is e to the 5th, u would be 5.
Yeah.
Yes, correct. So let's look at doing another example. Most of these you've seen before were the exact problem I assigned for U-substitution, but now you have bounds. So once you find the antiderivative, you have a choice to either change your bounds of integration or turn it back in terms of x and use your original bounds of integration. So let's look at this one, since it's a little more complicated than just a linear equation. So what is my u going to be here?
2 plus x.
2 plus x, right? So this is the less apparent U-substitution, right? We did an example of this where we get an x and a u, and we have to figure out how to write an x in terms of u from our relationship. So this is number 9. So if I integrate from -1 to 2 of x times the quantity 2 plus x dx. So would everyone agree x, or 2 plus x would be my u? And du is dx, which is nice because I can just interchange that. So method 1 would be to integrate x times square root of u du, and then plug in x equals -1 and x equals 2, and then write this in terms of u. What is x in terms of u? U minus 2, right? U minus 2 from here, right? So x equals u minus 2. And use my x bounds. That's method 1. Method 2 would say go ahead and change my bounds of integration. This would be, when x is -1, what is u? 1. And then when x is 2, what is u? 4. So then I still have u minus 2 times the square root of u du. But now I never have to go back in terms of x. I can just find the antiderivative in terms of u and plug in my u bounds. Question?
You put in -2 to, or -1 to what u equals to x into there, or where do you put it?
Right here. This is my relationship between u and x. So if x is -1, u would be 1. Because 2 plus -1 is u. And that's your u bounds.
Do we normally solve for x like that?
Not normally. This is a less apparent substitution where we do solve for x. But if this was, let's say, x squared, then when we differentiated it, we would get 2x dx. So we wouldn't have to solve for x because we would plug in a 2 here, 2x dx would become du. But when you're left with something like this, where you have an x and a u, you have to rewrite your x in terms of u. And in the case it's linear, you can always solve for that.
And so here it's not, because normally when I always see a square root, I normally turn it into 1/2.
You would still do that here.
Okay.
Right? It's the same thing. But now I can't integrate this until I distribute this through. Right? Because I can only integrate u to a power. I can't integrate a function times a function unless it's a perfect chain rule. So my bounds of integration are going to stay the same. U goes from 1 to 4. What's u times the square root of u? Yes, u to 3 over 2 minus 2u to the 1/2 du. Right? So here I would have u to the 5 over 2 divided by 5 over 2 minus u to the 3 over 2 divided by 3 over 2. And I can plug in my u equals 1 to u equal 4. Does everyone follow me on that? So I integrate, u to the 3 over 2 would be 2u to the 5 over 2 over 3. Sorry, 5. U to the 5 over 2 divided by 5 over 2, but I flip and multiply that, so it's multiplied by 2 over 5. And I integrate minus 2u to the 1/2, which would be 2 times u to the 3 over 2 divided by 3 over 2, but I flip and multiply that. Now I can use my u bound. So then this would be 2 times 4 to the 5 over 2 divided by 5 minus 4 times 4 to the 3 over 2 divided by 3 minus 2 over 5 minus 4 over 3. Right? So whatever this is minus whatever this is. Method 1, I found my antiderivative, but here I'm going to turn it back in terms of x. So see method 1. Method 1. I would have 2 over 5, 2 plus x to the 5 over 2, minus 4 over 3, 2 plus x to the 3 over 2, but I'm going to plug that in from x equals minus 1 to x equals 2. Because I have a function of x, I can use my x bounds. But if I do, you can see I have 2 over 5. If I plug in 2, I have 4 to the 5 halves, minus 4 thirds, 4 to the 3 over 2, minus 2 over 5, 1 to the 5 over 2, minus 4 over 3, 1 to the 3 over 2. Do you see that this is the exact same thing I have here? I'm plugging in 2, but I'm really getting 4 when I plug that in. Because basically I'm just shifting it. And if I have my function of u, I use my u bounds. If I have my function of x, I use my x bounds. Either method is going to give you the exact same answer. So this would be 2 to the 5th times 2 divided by 5, 2 cubed times 4 divided by 3. So this is some fraction. And this is going to be the exact same thing. Does that make sense? Do you see both methods give you the exact same solution? Method 1, the book says, is say, okay, just pretend there's no bounds on it, and find your U-substitution, find your antiderivative in terms of u, and then replace all your u's with whatever your U-substitution was in terms of x, and use your original x bounds. Method 2 says, transform the whole definite integral in terms of u by changing the bounds of integration. Integrate in terms of u, find the antiderivative in terms of u, use your u bounds with your function of u. Never go back to x. Okay, so let's do this simple example. I want you guys to do this one and see if you guys get the same answer, and then we'll move on to chapter 6. So this is number 5 on Wiley.
Your notation is important.
You didn't think on integration here, so to say these two are equal is not really true. So you want to think about your method, I think, is fine. You just a little bit. So you're trying to just find the difference, right? And then you plug back for x values, which this is for y, right? Well, it's not a 2, it's a 1. Yeah, du is 2dx. So you need a 2dx to replace it with du. And so if you put it in 2, you have to pull out 1/2. If you solve for dx, you get du over 2. So if you replace dx, you get du over 2. So yeah. So if I plug in 0, oh, you just wrote it wrong. This is 2x plus 1. Yes. Yes. Correct. Yes. I should finish this and plug these. Yes. Yes. Let me just look at your notation.
So you're saying.
5.5 area. Yeah, because 5.5 is saying we're not going to use calculus as algebra. You have to be able to graph it. Then you have to know the formula for whatever shape you have. Especially in the circle.
Oh, that would be easier.
No, if you're doing this method, you've already changed your bounds. So now you can leave it as in terms of u. So by the then minus
On that one that we just did, how do we go from the original to 625
You see your u x,
put that into the
Except the 8.
so that's okay.
if you had put this back in terms of x, you would have used your original bounds. So you would have had 2x plus 1 before. So
You have a choice. Method 1 or method 2. So, but to say this equals this is not correct. You need to change the balance right now. You could say, yeah.
Okay, so you do all here to say this. So I would get 8 and 0 though, right?
You plug it in.
so much easier if you can
What you
widen them
Oh, gosh, okay.
sections.
So if
Yeah,
I plug in.
we got 4 digits in that, right?
If I plug in my
We've
0.
got 4
So
digits.
I talked to you.
Unstarted micro.
Plug in 0.
Then we'll have a website.
I have like
This is the
So to say this equals this is for me, and this would be
written
you.
homework due Friday.
Right.
From that.
Right.
But that's different than a while ago.
This is to replace what, yeah.
So then I have enough.
So, for the, say that if you plug these down here, and that creates that U, and then so then it's terrible, so then once you get here, yeah, yeah, that's fine. So, yeah, so you're saying, starting here, integrating this with here, like it's done like that.
No, I mean, there was something here. But you skipped one in between 5.1 and how much better than that.
Yes, because they're saying here you're integrating from you and you're Okay, so you guys are having some good conversation. And one thing I want to stress on this is notation. So you see, I'm saying I'm integrating this. This is going to equal this integral. And I transformed it to totally be in terms of u. I actually wrote 0 to 2 here, and then I had to correct myself because that is not correct. To say 0 to 2 of 2x plus 1 cubed dx equals 0 to 2 of 1/2 u cubed du is not correct. That is not mathematically equivalent, right? If you wanted to leave your bounds in terms of x, you could say 1/2 the integral of u cubed du, and then put x equals 0 to x equals 2 here. That will remind you that once you find the antiderivative in terms of u, you put it back in terms of x and use your original x bounds. Question?
If you wrote that wrong on a test, but you got the answer right because you just had the notation wrong, but you were keeping it as x, would you lose points even?
On the fourth exam, no. If you have this and I understand and I can follow it, you won't lose points. And on the final, I don't anticipate you losing points.
It just might mess you up.
It might mess you up, yeah. And it is something that we've seen. When you don't change your bounds of integration, that's basically what we're testing you on a problem like this. You'll have basic U substitutions, the indefinite integral. So can you write it back in terms of x? But in this question would be testing, can you identify it's a U substitution? And then do you know how to properly deal with the bounds? So a lot of times we just, okay, you got 78, we look at your work so you understand what you're doing. When you don't get 78 is when we go and kind of critique your work a little bit more. And you get points for identifying it's a U substitution. You get points for changing your bounds. You get points of writing your bounds in terms and so forth to see what exactly went wrong here.
Okay.
So yeah, you want to be clear to say that now this integral equals this integral, but this integral does not equal this integral because you're integrating along the u dummy variable u, whatever u is, but u is going from 0 to 2 when it should be going from 1 to 5. So anytime you want to deal with it in terms of x, drop the bounds. Or you can put some u bounds here, go back in terms of x, and use your x bounds. But I like to always tell myself what step I'm at by writing u equals 1 and u equals 5. That tells me I've already changed my bounds. I'm good in u. Once I have my antiderivative in terms of u, I use my u bounds. If you love putting your antiderivative in terms of x, you do that, you use your x bounds. And you're going to get the exact same thing.
So to find your new u bounds, you plug it into the u
Yes.
bound. Okay.
Yes. This is your relationship between u and x.
Okay.
Right? So if x equals something, you plug what x equals to get the u there. Most of them are pretty straightforward. This is an example of the less apparent one when this x does not cancel and you have to rewrite it in terms of u, and then you have to distribute. So this one's a long problem in itself, and then on top of that you have to deal with u bounds or x bounds. You're going to get the exact same calculations, you'll get the exact same answer. The way you get there might be an extra step if you write it back in terms of x. Okay, so I think just with more exposure and practice and getting used to writing those out and getting the answers will be beneficial. So we're going to move on to 6.1. And the whole idea of 6.1 is the area between two curves. So we're kind of getting into the applications of integration. So Chapter 5 has focused on the area underneath one curve. Right? So if I have a function f of x, and the bounds are on a to b, and I want to find this area, let's see if I can get this to go. This is what it means to integrate a function from a to b. I get the area underneath the curve. So this area is the integral from a to b of f of x dx. Do you guys agree with that statement and what that means from the picture? 6.1 is going to be the area between two curves. So let me just draw this one up here. F of x, and let's say I have g of x. And let's say I bound that from A to B. So I'm looking for this area between these two curves. So without looking at the theorem that's in the book, how would you guys guess to do this? Yeah, right? Right? If I find the area from A to B of f of x, I get this whole area. And if I find the area from A to B of g of x, I get this white area. If I take the whole area minus the white area, I get the gray area, which is exactly what I want. So it turns out 6-1, we're going to find the area here by integrating from A to B of f of x times f of x minus g of x. Of course, anytime we deal with a negative, we're going to be careful with distributing that through the whole function g of x. But that should make sense, right?
So does the rest of the stuff we're learning all kind of go together?
Yes. We'll learn 6-1 to find the area in between two curves. And then 6-2 will be volume. And what we'll say is we'll have this area and we'll rotate it about the x-axis. So then we have this shape, it's like a donut. And to find that volume, we'll set that up. So, yeah, they go together. So the nice thing about what we learned in Chapter 5 is if the area was below the x-axis, it was negative, right? The fundamental theorem of calculus took that into account. So let's just look at a few more pictures here. If I want to look at, let's say, a function f of x, and then let's say g of x looks like this. And let's say I bound that from A to B. So if I integrate f of x, I get positive, right? And if I integrate from g of x, I'm going to get a negative. But if I take a positive minus a negative, you're adding them together, right? So the area between these two curves computationally look the exact same than if they were both positive, right? Because if I divide this up here, I'm taking this area minus a negative area. So I'm adding it. When I take a slice of it, f of x minus g of x, but g of x would then be negative. So I'm really taking f of x plus g of x. But you don't have to worry about that. Your setup will be the exact same. You integrate from A to B of your top function minus your bottom function with respect to x. Today, we're only going to focus in terms of x. Tomorrow, we'll look at examples of taking slices in terms of y. Because area, it doesn't matter if I look at a shape in terms of x or if I flip it and look at it in terms of y. As long as I get my bounds correctly, I'm integrating in terms of my y-axis. I'm changing my function in terms of y and my bounds in terms of y. This is really going to come in handy in 6-2 when we look at taking shapes and rotating about the y-axis or rotating it about the x-axis. The volume is going to be different, right? If I have this shape and I rotate it about the x-axis, I get one thing. And if I rotate it about the y-axis, I get a different thing. And this has applications in mechanical engineering. If you need to machine a part and you come in here and you slice it and then you rotate that slice, you get different shapes. Like if you get a bell curve, or if you have a curve and then you rotate it about the x-axis, you can get a bell. You rotate it about the y-axis, you get a different shape. So we're going to look at integrating along the x-axis today, and then tomorrow we'll talk about the y-axis. And then on Wednesday we'll look at rotating things and finding volume. Okay, so one more picture I want to draw here. And let's say we have f of x, and then let's say we have g of x. And let's put our bounds of integration to go from A to B. Let's call this point C. And I want to find the area enclosed by these two curves from A to B. How would I set this integral up? Integrate from A to C and then C to B. Yeah. So if I want to integrate for the area, I'm going to integrate from A to C of what? F of x minus g of x with respect to x plus the integral from C to B of what? Sorry about that, guys. G of x minus f of x dx. So basically, the only thing new from 6.1 is you're going to have to set these problems up based on their graph, which is the above function minus the lower function. Now, this is just some polynomial. Integrating a polynomial straightforward, plugging in the upper bound minus the lower bound. Doing the same thing over here, adding those two areas together.
You're doing that because G of x is above f of x from C.
Correct. Yes. Right? It's always the top function minus the bottom function. Because the integral of the top function will give you this area. Minus this area gives you the gray area. Here, you have this area minus this area, which would be g of x minus.
So in a given interval, it's just whichever one is greater, basically.
Correct. Whichever one the y component is larger. So sometimes you have to find your own where they equal each other. So you have to find what value of x does this give you. So if I'm integrating from 1 to 5, and c happens to be a half, I'm integrating from c ends up being 5 halves, then I'm integrating from 1 to 5 halves of the top function minus the bottom function, plus from 5 halves to 5 of the top function minus the bottom function. So we're not going to have time to finish this one, but I'm going to go ahead and set this example up. So let's find the area of the region between y equals x squared, y equals x plus 6. Part A is going to be on 0 and 2, and part B will be on minus infinity to infinity. So here we're looking for the area of the region between these two functions on an interval, and the area of this region between two functions from minus infinity to infinity. So you have to come up with your own parts where x intersect, where the two functions intersect. So if I look at graphing this, I have a quadratic, and I have a line that has a y-intercept of 6. So for part A, this would be x plus 6, and this would be x squared. For part A, I'm integrating this region. I'm finding the area of this region. So I'm integrating from 0 to 2. But on part B, I have to find when these two equations equal each other, right? So I need to find when does x plus 6 equal x squared. So we don't have time to finish this one today, but if you want to look over it, convince yourself, try to do it by tomorrow. Tomorrow we'll do both these examples and then look into, we're taking slices about the x-axis. So we're integrating on the bounds of the x-axis. My functions have to be a function of x. But sometimes it's easier to integrate along the y-axis and take slices of y. Then you have to look at the outermost function minus the inner function. This one's not easier to do in terms of y, but we'll look at some that are. All right, I will see you guys tomorrow.